Good afternoon. I'm Professor Sever. Today we're going to discuss analytical techniques for evaluating limits in Calculus 1. Okay, so we have two theorems. These are very nice theorems. If p is a polynomial function and c is a real number, then if we're considering the limit as x goes to c of p of x, that's simply p of c. Notice the key here is, how do we evaluate the limit of a polynomial? Through functional evaluation. And of course that will justify what we just spoke about here. Using that theorem, rather than breaking the problem up into its constituent components, which is slow, this theorem says, illustrating it here, if p is polynomial and I'm considering a limit, I may evaluate this limit simply by plugging in. Much quicker, much more elegant. And the same holds for a rational function, which is the ratio of two polynomials, where c is in the domain. Notice it says q of c is not 0. That implies c is in the domain of R. And in this case, if you're evaluating the limit of a rational function where c is in the domain, you may evaluate that limit simply by plugging in, which is what the theorem says. And here's an illustration. Notice I have a rational function here. The ratio of two polynomials is the number 1 in the domain, certainly because the denominator is non-zero. So in this case, how would I evaluate the limit? The limit is evaluated simply by functional evaluation, namely you plug in. So we plug in and we get the result of 4 over 2, which is 2. Very nice. Radicals. Polynomial functions and rational functions are two of the three basic types of algebraic functions. They're probably the first two nicely defined functions. The next theorem deals with the third basic type, which is radicals. Again, there's no real order here. We could have done something else first, perhaps absolute value, but this is a simple, we're just progressing along a certain path. The first one is the odd radical functions. So we would be discussing cube root, fifth root, etc. And notice again, this is a very nice theorem. It says that if you're evaluating the limit of a radical function with an odd root, you do so by plugging in. For the even indices for the radicals, it's not so easy. First off, we would never plug in a negative number for an even radical. You can't take the square root of -1. Well, you can, but not in terms of the real valued functions of a real variable. We're not dealing with complex numbers here. So that would tell us very quickly we wouldn't be considering the negative values of c. But what about 0? Well, as I mentioned previously, for these even index radicals, the 0 is an endpoint of the domain, and therefore those limits wouldn't exist. So if c is positive, then you can plug in, if c is positive, you can evaluate the limit of an even index radical simply by functional evaluation. So again, our primary theorems for evaluating limits are resolving themselves into functional evaluation. Again, we're considering the nicest of cases. We're presenting these theorems first. And we have an illustration. The limit as x goes to 4 of the square root of x. Well, 4 is positive. Square root of x is an even index radical. Remember, we don't write the 2. We don't have to write the 2 for the square root function. And since 4 is positive, we may evaluate this limit by functional evaluation. Namely, we just plug in, so the result is 2. Okay, now, much more complex theorem than this one is very nice. The next theorem greatly expands our ability to evaluate limits because it shows how to analyze the limit of a composite function. So first, before I discuss the theorem, let's look at the coming example. I want to evaluate the limit as x goes to 0 of the square root of x squared plus 4. Well, first off, there's a couple of issues here. 0 this is an even index, and 0 is not positive. So by the prior theorem, we couldn't apply the prior theorem if you were wondering, on two grounds. One, this theorem doesn't tell us what to do if c is 0. It doesn't say the limit does not exist. Rather, it just says what happens when c is positive and you have an even index radical. So this theorem cannot be applied to this problem on two grounds. One, c is 0, and two, this is not just simply the square root of x. you have a composite function here, as we see. The inside function is x squared plus 4. The outer function is the squaring function. So we see that this function here is written as the composite of two functions. And that's precisely what this theorem is designed to do. So at this point, before attempting to use this theorem, or before proving it, how would we evaluate this limit? Well, we would struggle. We wouldn't have a theorem to do it. We would have to use the epsilon delta definition, which wouldn't be all that bad, but we also know it's probably not that fun either. Okay, so let's look at the theorem. And it's designed to work in certain cases when the criteria of the theorem is met for composite functions. So if f and g are functions such that the limit as x goes to c of g of x is L, g is the inner function, and that in this case this would be x squared plus 4. So if the limit of the inner function at c is L, that says the limit exists and is L, and the limit of the outer function, the limit of f of x at L, not c, note, not c, the limit of f of x at the outer function is f of L, then you may evaluate the limit of the composite by plugging in. It's just f of L. Got it? You see this, it's the limit here. This is a sufficient condition for evaluating the composite. This is not a necessary condition. In fact, the reverse wouldn't be true. Okay, in all cases, we could easily come up with a counterexample. Let's look and see how this theorem was applied. So, f of x equal square root x is the outer function. The inner function is x squared plus 4. So what's happening to the inner function? We need to look at that. As x goes to c of the inner function, we need to see if that exists. So, of course it does. That's a polynomial. So how do we evaluate the limit of a polynomial? We just discussed that, functional valuation. So the limit as x approaches 0 of g of x is simply achieved by plugging in to x squared plus 4, and that's just 4. And that's the L, so L is 4 in the theorem. Okay, now what we have to do is evaluate the limit as x goes to 4 of the outer function, which is the square root of x. And by the way, that was the previous example that we just discussed a few minutes ago. So the limit as x goes to 4 square root of x is the square root of 4, which is 2, and of course this is f of 4. Note that f of 4 is 2. So we now have the limit of the outer function evaluated at L, and the key here is not that it exists, but it exists and matches the functional value. So you get the limit by plugging in, or rather it matches the functional value which happened. Therefore, the limit of the original problem is f of L. That's 2. And we'll do more of these problems in the homework. This is a very potent theorem for us. Trigonometry. This is a calculus course which is predicated on both algebra, trig, and pre-calculus, so we will be using the trigonometric functions extensively throughout this course. So this 6-part theorem says, loosely, well it says actually specifically, says if c is in the domain of the trig function, and we have 6 of the basic trig functions here, then if you're evaluating the limit of that trig function, it's simply achieved again very nicely through functional evaluation. So quickly, in each of these 6 cases, what we're saying is if c is in the domain of sine, then the limit as x approaches c of sine x of sine of c. And namely, this limit is achieved through functional evaluation. The same for cosine, the same for tangent, namely, if c is in the domain of tangent and you were considering the limit as x approaches c of tangent x, then you would know that that limit would be equal to tangent of c. The same holds for cotangent, cosecant, and secant, again, if c is in the domain of each of these functions. This theorem does not say what happens if c is not in the domain. Well, and in the case of sine and cosine, that's not possible because the domain is all real numbers. So we know, for example, that the tangent of pi halves is undefined. Rather, pi halves is not in the domain of tangent. So this theorem does not say what happens to the limit as x goes to pi halves of the tangent of x. In fact, but we'll be able to show using another result that that would be undefined. So let's look at the positive results. What happens? 3 examples when c is in the domain. Let's look at the first case. The limit as x goes to 0 of tangent x. So we ask ourselves, is 0 in the domain of tangent? The answer is yes. So that this limit is evaluated by functional evaluation. Okay, and again, notice on this step, there's no limit here. Why? Because I'm plugging in. Going from here to here, I'm evaluating the limit. Therefore, the limit, you don't see the limit here because we're evaluating tangent at 0, and by this theorem, that is the value of the limit, which is 0. Okay, let's look at this one. Now, technically, we have to go think about that product, the technical limit. The limit of the product is the product of the limits, which is this theorem. Okay, if the limit of both of the f and g exists at the same c value, then you can evaluate the limit of the product by separating it and looking at the product of the 2 limits separately. So the limit of the product is the product of the limits. So the product here is written here. So now the limit as x goes to pi of x is simply pi. The limit as x goes to pi of cosine x is cosine pi. And so now, of course, we evaluate both of these 2 limits separately through functional evaluation. And the final answer is the product of pi times cosine. Of course, the final answer is the product of pi times the cosine of pi. Of course, the cosine of pi is -1, so this answer is minus pi. Finally, the third example. Now, notice these are the basic trigonometric limits. Sine squared is not in here. So how do we evaluate the limit as x goes to 0 of sine squared? Again, using the same theorem, we can do actually we're using the other version of the theorem. Let's go back. We could do this 2 different ways. We're using the power rule version. So if the limit as x goes to c of f of x is L, and you were looking at the natural number exponential of f, then you could evaluate the limit again by simply exponentiating the limit as x goes to c of f of x, which is L. And that's what we're doing here. So the limit as x goes to 0 of sine squared x is the limit as x goes to 0 of sine x squared. Now this is the f in the problem. See, now we can apply this one to this one using that previous theorem. And what is the sine of 0? Is 0, and that's simply 0 squared. And again, you might say, hey, all 3 of these cases, even though I showed the work here through using 2 of the previous theorems, were achieved by functional evaluation, and that would actually be right, because these functions, as we will come to learn, are actually continuous functions at the individual c values at hand. These 2 functions are in fact continuous everywhere.